y bar. Okay, just to make matter clear. Okay. So from here, you have to be very careful now. So y205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.8 power minus 3 times by 0.166. So it's equal to 189.22 times 10 to the power minus 6. Let me do it again. 0.205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.8 power minus 3, 11.8 power minus 3 times by 0.166. And I do, okay. And then you plus 0.205 divided by 2 minus 11.8 power minus 3. And then you can square it times by 0.5 times by 7.2 power minus 3. So it's equal to 39.615 times 10 to the power minus 6. Let me do it again. 0.205 divided by 2 minus 11.8 power minus 3. Square the whole thing. Times by 0.5 times by 7.2 power minus 3 is equal to 29.615. So we have our Qx, right? So 189.22 plus by 29.615 is equal to 218.835 times 10 to the power 6 meter cube. Let me do again, 189.22 plus 29.615. Yep. Okay. So from here, we can finally calculate what is our shear stress. So I'll take the whole thing again. Compute our shearing stress. So we know that shear xy, shear zy will be equal to 25 times 10 to the power 3 multiplied by 218.835 times 10 to the power minus 6. Okay, I think down here I'm missing my minus sign. Then divide by 40.9. Okay, and then the thickness is 7.2 now. Okay, so this is equal to 25 power 3 times 218.835 power minus 6 divided by 40.9 power minus 6 divided by 7.2 power minus 3 is equal to 18.578. Okay, 18.578. Okay, times 10 to the power 6 Pascal. Okay, so that is our shearing stress, and the direction is going to be in this direction. Okay, so from here, let me get rid of this part. What have we accomplished again? Is we have our element B, right? So element B, now the orientate change to this direction. So we know on element B, our normal stress is now in compression, minus 14.996. And then we have our shear in this direction, and this is equal to 18.578 times 10 to the power 6 Pascal. Okay. Then if we were to sketch out Mohs circle, it will look not exactly the same like this now, okay? Because now you have it in compression now, right? So I'm going to do a very quick sketch now. So if I have to label, so now this is our X, this is our Y, and this is our Z. So we will call this our point Y. This is our point Z. and then this is our point X. So you can see how things changes. So if now we were to sketch our mole circle, we are going to now focus on the compression region now, right? So this is our normal stress, shearing stress, and we know now over here, our point X is here, okay? And then we are going to have our okay. So this is our normal stress in Z, is in compression. And then we have our shearing stress. Okay. Now we have to draw 3D mole circle because we want to know which is the biggest circle, because the biggest circle is the one that's most important. Okay. So from here, if we were to, so the element have to go clockwise and anti-clockwise. So from here, Z, the element will rotate clockwise. So this is your point Z. And now this is your point Y. It's different from the one before, right? The one before, point Y is at 0, right? Point X is here, point Z. So this is different now, okay? So now you sketch your 3D mole circle. So this is one of your circle, right? So this belongs to your YZ plane. Now, when you draw mole circle, don't forget to draw this line. There are students that forget to draw this line, and I minus the mark. Okay, don't forget to draw this line. And then you have the other two circles coming in now, right? So this is for your X, Y plane. And then the last circle, as I say, this is to ensure that you're analyzing the biggest circle. Okay, but you have to show me that you're analyzing the biggest circle. Okay. So this is your, over here, this is your what? This is your X, Z plane now. So now you realize that we are going to use the stress mean value. Okay, not your stress max now. You can see how it changed now. Okay, so bear with me, give me like another like 5 minutes. Okay, then we go for a break. So from here, I'm going to, so we know that this is our stress average. So we are going to calculate our stress average. So center of circle. So our stress average will be equal to stress Y plus by stress Z divided by 2. Okay. So this will be equal to minus 14.996 times 10 to the power 6 divided by 2. So minus 14.996 power 6 divided by 2 is equal to minus 7.498 times 10 to the power 6 Pascal. Then our radius of circle. For this case, is our tau max. So this happens to be equal to minus 7.498 times 10 to the power 6 squared plus by 18.578 times 10 to the power 6 squared. Okay, so this will be equal to 7.498 power 6 squared plus by 18.578 power 6 squared. Square root of the whole thing is 20.034 times 10 to the power 6 Pascal. Let me do again, 7.498 squared plus by 18.578 squared, square root 20 by, right? So down here, we know that stress max and mean is equal to minus 7 point, or stress max, okay, let's do stress max first, is equal to minus 7.498 times 10 to the power 6 plus by 20.034 times 10 to the power 6, right? So 7.498 plus 20.0 minus 7.498 plus 20.034 is equal to positive 12.536 times 10 to the power 6 Pascal. Okay. And then this is where you have to use the minimum value because the stress mean magnitude is higher. Okay. 498 times 10 to the power 6 minus by 20.034 times 10 to the power 6. So this will be equal to 10.498, 20.034 minus 27.532 times 10 to the power 6 Pascal. And then your tau max will be equal to 20.034 times 10 to the power 6 Pascal. Then if we were to calculate our factor of safety, now we are going to, the value that we used earlier is 345. So use the same value as 345. But you divide by minus by what? 27.532. Okay. So absolute value is equal to 12.53 factor of safety. Okay, 345 divided by 27.532. Okay. So you can see like the detailed analysis. Okay. So go for a 10 minutes break. We come back, we do the last topic on yielding. Okay. See you in 10 minutes time.